Alright, so yesterday's work had to do with some more straightforward or some of the most basic applications of Ohm's law, which we can sort of boil a lot of problems down to. And the equation still remains the same. I have here the version of Ohm's law that you'll usually see in a textbook, or if you Google Ohm's law, usually it'll show this V equals IR equation. But I also wrote here the version of it that I tend to prefer as a conceptual tool for us, which is that I, the current, is equal to a voltage divided by resistance. Just because I think usually in terms of current and the flow of electrons being directly proportional to a voltage and inversely proportional to a resistance, which means that if we increase the voltage or the power of our battery, electrons are going to flow faster and we'll get more electricity in our circuit. And if the resistance goes up, then we'll have less current flowing through. So our denominator gets bigger for that resistance. That'll decrease the overall number, or it'll slow the flow of those electrons, which is current. Okay, now the problems that we're trying to solve today they are very similar to the ones that you all solved yesterday. So let's go over a problem where we initially have, let's say, 10 ohms or a 10 volt battery, 10 volt battery. And let's say that we have 4 amps of current running through this circuit. So you've used your ammeter and you measured that the current running through this circuit with this 10 volt battery and whatever resistor we have, we measured that current to be 4 amps. And the question for us is, if we wanted to double the current, so get electrons flowing through this system twice as fast as they were before, we want to double that current, what does the new resistance need to be to make that happen? So here, since we don't have any mention of voltage or voltage changes here, we just see that current and resistance are changing, or something about this new resistance. I'm going to assume that the voltage of our battery is not going to change. So we want to keep the exact same battery we were using before, the same 10 volt one, but we want to double the current by changing something after that battery, something in the resistors in our circuit. And so there are a couple different ways to think about this. I'm going to show my preferred way, but again, there are definitely multiple ways to solve these problems. So if you have your own way to do these, I would always encourage you to stick with those. It'll be a much more meaningful way to solve problems for you. So we have doubling the current. So first thing I'm going to write is that our new current now is 8 amps, right? Double this 4 amp current would be 8 amps. And since I said we're keeping the same battery as before, I'm going to write that our battery is still 10 volts. The voltage here is still 10. And now if we want to solve this so we don't know what the new resistance is, then this now that we've made this manipulation from 4 amps to 8 amps, now this problem looks like what you all have solved yesterday. So I'm going to plug in the stuff that we know. 10 for our voltage, V. 8 is our current, I, and then we don't know our resistance yet, but we're going to solve for that now. And we have 8 being multiplied by R, so if we want to isolate the R, because we care about what the resistance is, I'm going to divide both sides by 8. Division, opposite of multiplication, should cancel out these 8s, and then I need to do a 10 divided by 8 to find what our new resistance needs to be. So 10 divided by 8 should be 1.25. And since this is a resistance, our units are ohms. So we could figure out how we could manipulate this system to maybe provide twice as much power, twice as much current to this circuit. Now I'll do one more example of these, but honestly all of these problems can sort of be boiled down to the same use of Ohm's law. It just requires some problem solving, some critical thinking, as one sort of preliminary step before we start plugging in and solving this mathematically. So let's say instead that we wanted to double the current by instead changing the voltage provided to the circuit. So now we're leaving whatever light bulb or some application, whatever is providing resistance to our circuit, we're not changing that. We're only going to change this 10-volt battery to something, to whatever it needs to be to double this current. So I think probably the easiest way to do this is to first solve for the resistance that is not changing. Here in this situation, now we're being asked about a changing current and some changing voltage. So I'm going to assume in this case, not in all of these problems, I didn't do this in the last problem, but we're going to assume that the resistance is constant. And again, the reason that I'm assuming resistance is constant in this problem is because we're told that current is changing, right? We're doubling the current, and we're asked about what this new voltage needs to be. So voltage and current are changing, but we're going to assume that we leave the other piece of Ohm's law constant, so resistance. In the last problem, we were changing current and resistance, so I assumed voltage was constant. It depends on sort of what the question being asked of you is, based on what you assume is constant. So let's go back up to this green preliminary situation, and let's solve for whatever this resistance is. So I'll plug in the stuff that we know. 10 is the initial voltage, 4 is the initial current, I, and we don't know what this R is. So we want to isolate this R resistance. So I'm going to do the opposite of whatever is happening to it right now. It's being multiplied by 4 right now. And if I want to get rid of that 4, I've got to divide both sides by 4. So these 4's will cancel out. Then we would do 10 divided by 4 and get that the resistance there is equal to 2.5 ohms. And again, the reason that that's helpful for us is because this resistance, we are assuming, is still going to be true down here in this yellow situation. So let's go ahead and finish this problem now that we know that our current still needs to be doubled. So it used to be 4 amps. Now we want that to be 8 amps. And our voltage is changing, but our resistance is still remaining the same 2.5 amps that it was before. And we just don't know the voltage. So let's plug into Ohm's law. We don't know this V voltage, so I'm going to leave that as a variable. We've got 8 amps here as our current, and then for our resistance, again, we know that it's the same 2.5. Maybe you already noticed this, but I made a mistake in writing amps as our unit for resistance, but it would be 2.5 ohms as our unit for resistance there. And then if we multiply these two, 8 times 2.5, that should get us, I believe, 20 volts as our final voltage, our final electric potential difference for our battery. Now, one thing I want to point out is if we wanted to double this current, this 20 volts is twice as much voltage as our initial current. So the reason that I like this equation, this I equals V over R, is because if you know about these relationships about voltage being directly proportional to current and resistance and current being inversely proportional, which means if resistance goes up, current goes down, then you actually could have done these in your head partially. If voltage doubles and resistance doesn't change, then current doubles. If voltage triples and nothing happens to resistance, voltage triples, then current is going to triple as well. If we cut this voltage in half, then our current will be cut down by a half as well. And then for resistance, whenever resistance is doubled, right, if we double our denominator, that's like cutting our current in half. And if we tripled our resistance in the denominator, that would cut our current by a third. So when we needed to double our current before, we basically needed to cut this resistance down by a half, and that was when we got 1.25 ohms was the change that we needed to make if we just wanted to change our resistance. So whatever happens to voltage happens to current, just like it would for a numerator. But for our denominator, whatever happens to resistance, the exact opposite happens to our current. So these are some slightly more complicated ways to use Ohm's law and relationships shown here, but if you have a strong grasp of what these relationships are shown or are showing, then I think you'll be able to solve these problems even without some of these math steps that I did here.